Today we are going to learn about mastering NumPy concatenation for data analysis. We will explore efficient techniques for array concatenation using NumPy, crucial for data manipulation and preparation in analytics workflows. Welcome to our video on mastering NumPy concatenation for data analysis. In this session, we'll delve into the world of NumPy, a powerful library in Python that is indispensable for numerical and scientific computing. One of the core functionalities that NumPy offers is array concatenation, an essential skill for data manipulation and preparation in analytics workflows. Concatenating arrays allows you to efficiently manage and prepare data, enabling smoother data analysis processes. By the end of this video, you'll be equipped with the knowledge to handle complex data structures effectively, leveraging concatenation techniques that are optimized and suitable for real-world applications. Let's begin our journey into the depths of NumPy concatenation. In this section, we will explore the core functions used for concatenation in NumPy: np.concatenate, np.vstack, and np.hstack. Each of these functions serves a unique purpose. The np.concatenate function is versatile and allows you to concatenate two or more arrays along a specified axis. It's the most general form of concatenation in NumPy. On the other hand, np.hstack is specifically for vertical stacking, essentially stacking arrays rowwise, making it ideal for combining datasets of similar features. np.hstack, as the name suggests, is used for horizontal stacking, which is column-wise concatenation. This can be particularly useful when you have datasets with the same number of rows but different features. Understanding the differences between these functions and their specific use cases is crucial for choosing the right approach depending on your data structure and the analysis you are conducting. We will look into examples that highlight the strengths and weaknesses of each function to give you a comprehensive understanding. Now let's focus on concatenating 1D arrays. A 1D array in NumPy is essentially a simple list of elements. It's straightforward to concatenate these arrays using np.concatenate. You simply pass a list of arrays you want to concatenate, specifying the axis if needed. However, since we are dealing with 1D arrays, axis specification is generally not required. Additionally, np.hstack can be used for 1D arrays to achieve the same result. Let's look at a practical example. Suppose you have two 1D arrays, one containing customer IDs and another with corresponding sales figures. By concatenating these arrays, you can create a more comprehensive dataset for analysis. It's important to ensure that the arrays are compatible in terms of dimensions and data types, otherwise, you might encounter errors. A common mistake to avoid is mismatching dimensions, which can lead to unexpected results or runtime errors. By understanding these basics, you can manipulate and prepare your 1D data more effectively.
Moving on to 2D arrays, which are essentially matrices with rows and columns. Concatenating 2D arrays is slightly more complex than 1D arrays, as you need to consider the axis along which you want to concatenate. Using np.concatenate, you can specify axis equals 0 for row-wise concatenation or axis equals 1 for column-wise concatenation. With np.vstack and np.hstack, you can easily perform vertical and horizontal concatenations without specifying axes. Let's say you have two datasets, one containing employee information and another with department details. By concatenating these datasets along the appropriate axis, you can create a comprehensive data table for analysis. It's crucial to ensure that the dimensions match along the axis you are not concatenating. For example, when concatenating along rows, the number of columns must match. This section will provide practical use cases and tips for handling dimensions correctly to avoid common pitfalls.
In this segment, we explore the intricacies of concatenating ND arrays, which are arrays with more than two dimensions. ND arrays are common in fields like image processing, where data might have dimensions representing width, height, and color channels, or in deep learning, where tensors might represent batch sizes, features, and time steps. When concatenating ND arrays, understanding and correctly using the axis parameter becomes even more critical. For instance, if you have two 3D arrays representing different batches of data, you might want to concatenate along the batch dimension to combine them into a single dataset. Advanced examples will illustrate how to manage these complex structures, ensuring that you maintain data integrity and avoid errors. Best practices include verifying the shape compatibility along each dimension and understanding the implications of concatenating along different axes. Mastering ND array concatenation is a powerful skill that can greatly enhance your data manipulation capabilities in complex scenarios. One of the challenges you might encounter when concatenating arrays is mismatched dimensions. NumPy's broadcasting rules allow operations on arrays of different shapes, but concatenation requires careful handling to ensure dimensions are compatible. Mismatched dimensions can be resolved using the reshape function, allowing you to adjust the dimensions of arrays before concatenation. For instance, if you have a column vector and a row vector, you might need to reshape one to match the other's dimensions. This section will delve into the intricacies of broadcasting in NumPy, providing practical solutions and examples to handle dimension mismatches effectively. Understanding these rules and techniques is vital to avoid common errors that can arise from incompatible shapes. By mastering these skills, you can ensure smooth and error-free concatenation processes, making your data preparation more robust and efficient. Performance is a critical factor when working with large datasets and complex operations in NumPy. Concatenating large arrays can be memory-intensive and slow if not done properly. Efficient memory usage is crucial, and one way to achieve this is by using in-place operations where possible. This minimizes the need for additional memory allocation. Additionally, avoiding unnecessary copies of data can significantly enhance performance. For instance, instead of creating new arrays during concatenation, you can modify existing ones directly. This section will provide optimization tips and best practices to improve computation time and memory usage, making your NumPy operations faster and more efficient. Understanding these performance considerations is essential for data analysts who deal with large-scale data and require efficient workflows. Even seasoned data analysts can fall into common pitfalls when concatenating arrays using NumPy. One frequent mistake is specifying the wrong axis, leading to unexpected results or errors. It's crucial to understand the structure of your arrays and specify the correct axis for concatenation. Incompatible data types can also pose challenges, as NumPy requires consistent data types for concatenation. Ensuring shape compatibility is another common issue. Mismatched shapes can lead to runtime errors. Memory overflow can occur when working with extremely large datasets, so it's essential to monitor memory usage and optimize performance accordingly. This section will provide debugging tips and tricks to help you identify and resolve these common pitfalls effectively, ensuring smooth and error-free concatenation processes.
In this section, we'll explore real-world scenarios where NumPy concatenation is applied. Data integration is a common task in analytics workflows, where you need to combine data from different sources or formats. For example, a retail company might have separate datasets for online and in-store sales. Concatenating these datasets allows for a unified view of sales performance. In healthcare, patient data from different departments might need to be combined for comprehensive analysis. This section will showcase practical use cases and industry-specific applications of NumPy concatenation, demonstrating how it facilitates data integration and enhances data analysis capabilities.
Maintaining data integrity is paramount when concatenating arrays, especially in data-intensive fields. Ensuring data consistency involves validating data before performing concatenation operations to prevent errors. It's important to check for missing data and handle it appropriately, either by imputing values or excluding incomplete data. Documenting data transformations is another best practice, helping you track changes and maintain a clear audit trail. Quality assurance techniques, such as cross-validation and data checks, ensure the accuracy and reliability of your concatenated datasets. This section will provide guidelines and strategies to maintain data integrity, ensuring that your data remains consistent and reliable throughout the analysis process.
As we conclude our session on mastering NumPy concatenation for data analysis, let's recap the key points. We've explored the fundamental functions for array concatenation, the differences between np.concatenate, np.vstack, and np.hstack, and practical examples of concatenating arrays of various dimensions. We've also highlighted the importance of handling mismatched dimensions, optimizing performance, and maintaining data integrity. Mastering these skills is crucial for efficient data manipulation and preparation in analytics workflows. We encourage you to practice these techniques and explore further resources to deepen your understanding. Thank you for joining us, and we hope this video has equipped you with valuable skills for your data analysis journey.